Hi everyone, my name is Stuart Gilmore. I'm Professor of Biostatistics at the Graduate School of Public Health in St. Luke's International University here in Tokyo, Japan. This is my first YouTube video. I'm going to give a presentation that I gave about 2 weeks ago at the EcoSta conference in Tokyo. This presentation is a simulation study of the way that economists use mortality modeling to study policy interventions in public health. I think it's of particular interest if you're a PhD student who's looking to use mortality data as part of an econometrics or economics study, or if you're someone in public health who is concerned about whether or not econometrics analyses are correctly handling public health data. So as I mentioned, this is my first YouTube video. I intend to present some more lectures and studies on YouTube over the next couple of months. And I hope that the quality of the videos and my presentation will improve as I get used to this format. This is the basic format I use for lectures. I have removed the logo of St. Luke's International University from this presentation because I'm putting it on my YouTube channel. But I did this at the Economics and Statistics Conference 2 weeks ago in Tokyo. Okay, so let's start by talking about why we need to discuss the work that economists do in public health, and then I'll show you what I did. So you will have noticed, I think, that in the last decade or so, econometric studies of public health issues have become more common. So econometricians have been approaching various problems in public health and analyzing public health data to try and understand the impact of policies and interventions on those issues. Now, many of these studies use mortality data. For example, Case and Deaton have done a lot of work on deaths of despair, which is so-called deaths of despair, where they use mortality data for white people in America. And there have been some studies, for example, of open defecation and child mortality in India. And there has been a slew of recent studies looking at the role that naloxone distribution plays in preventing or encouraging opioid overdose deaths in America. Now, most of these studies don't use formally correct statistical techniques. And there's actually no agreement on the methods that should be used for analyzing mortality data among economists. So in every paper you see from an econometrician that looks at public health data and mortality data in particular, you'll see a different approach, a different way of defining the model, a different way of handling the response, and a different way of interpreting coefficients. Now, this is in stark contrast with statistics and epidemiology, where there's a well-established approach to using mortality data, and there is a formally correct method for approaching death. And my interest is in what the implications are of this statistical incoherence for the policy prescriptions that econometricians make. For example, in their studies of naloxone distribution, they tend to conclude that naloxone distribution is associated with an increased mortality rate from opioids. But if they're using a formally incorrect model, are their results actually consistent with that finding at all? Or have they just found arbitrary results that don't actually reflect reality in any way? So I'm interested in finding out whether or not that is a problem and what the consequences are for their policy prescriptions. So let's just briefly review the formally correct way of handling death data and compare it with methods that are used in econometrics. So the formally correct way to analyze deaths is to treat deaths as a count, that is, as a discrete number that's greater than or equal to 0. However, in econometric methods, there is no consistent way of handling the response. So sometimes it's a rate, sometimes it's a count, or sometimes a log of a count. It's difficult to find a coherent single response. In the formally correct way, we should treat the count response as a Poisson distribution with some mean. But in econometric methods, the response is always treated as a normal distribution. That is a Gaussian distribution. In the formally correct approach, we have a log link function, which links that mean which drives the Poisson distribution to a linear expression. But in econometric methods, the link function is arbitrary. It can be the identity, can be a log. Sometimes it's an inverse hyperbolic sine transform. It's arbitrary. In the formally correct approach, we use population as an offset in the model. That is, it enters the model as a covariate with a fixed coefficient of 1. However, in econometric methods, the population enters as itself as a covariate and sometimes logged and sometimes in its natural form. Also, econometric models frequently have an arbitrary choice of weights. They might input the population as a weight, or they might put the log of the population as a weight, or its square root. It's quite arbitrary. Now, in the formally correct approach, we can interpret the coefficients of the regression model as a rate ratio. That is, if we exponentiate a coefficient, it gives us the rate ratio associated with a unit increase in the covariate. However, in the econometric approach, there is an arbitrary interpretation of coefficients because there's an arbitrary link function and there's different ways of handling the covariates in the model. And this can lead to consequences. For example, if somebody does an econometric model with, for example, an inverse hyperbolic sine link function and the log of population as a covariate, then when they present a coefficient for, say, a treatment intervention, we don't actually know whether that coefficient can be interpreted in a clean and simple way as, for example, a positive value means a positive change in the outcome. We need to be more careful with it. And I'm not sure that any econometrics paper has ever explained how to interpret the coefficients of their models. So let's see what we get with our application of these models to some simulated data. And that is my objective. So first of all, I conducted a literature review of a range of models that are used for analyzing mortality data. Then I wanted to apply these models to simulated data. So I wanted to generate some simulated data where we know the truth, and I wanted to apply the models from econometrics to that simulated data and compare them with formally correct models. And then finally applied the models to some real life data with a clear structure so that we can see whether the econometric models compare with formally correct statistical models for analyzing real life data. And once I've done these three things, I want to ask some questions about the implications of this statistical incoherency in econometrics for the policy prescriptions that arise from this field. So now let me go through the methods, what I did. Halfway through this, I'm going to pause and show some R code and some Stata code and some data, which I didn't do in the EcoSta conference because I only had 15 minutes to present. So my basic approach was, first of all, to review the literature and then to generate some simulated data. So for the review, I searched the National Bureau of Economic Research database for policy studies. The NBER is a members-only organization which publishes working papers of different aspects of economics on the NBER website. It's useful because those papers are free to access. And also it's instructive because the members are generally accepted to be the most well-respected and highest achieving people in the economics field. So we should expect that the studies there are exemplars of how economists use mortality data. So I did a review and I included any studies that used mortality as a primary outcome in a statistical analysis, not just like a descriptive study and not one of the studies that does like a mathematical, formal mathematical model, but a statistical approach. From the studies I found, I extracted the details of the models from the main text and the tables, and I categorized the models with the main examples of how they're used. So I categorized the models according to like how they handle the response, what is the link function, how do they handle population, the various elements in which econometric studies tend to differ from each other. And then I presented them with an example of each study. So that was the review. For the simulation, I simulated data in R, which was a varying sample sizes, either 20, 100, 200, 2,000, or 20,000, with with a set of control units and a set of treatment units. I assumed equal numbers of people in the treatment and control groups, and I modeled a null effect in all of these studies. So if there was a particular rate of death in the control group, I assumed that the rate would be the same in the treatment group. I then varied the population in the treatment group to be between 1 and 2 times the size of that in the control group. I set the base population in each observational unit in the control group to be 1 million, and then I varied that between 1 and 2 million in the treatment group. The reason I did this is because I suspect that a lot of these models that include population as a covariate have very weird behavior once the populations differ between treatment and control groups. Now, a treatment group having double the population of a control group, it's not so unusual when you think about the kind of policy studies that are being enacted. In fact, it's quite a small difference. So if you imagine, for example, that you're doing a study comparing mortality rates in smokers with non-smokers in the adult population, smokers in most countries are between 10 and 20% of the population, which means that your treatment group has a size 1/5 to 1/10 of your control group, a population size. If you're studying naloxone and you're looking at naloxone distribution, then because naloxone distribution is expensive and complicated, your intervention group may be much, much smaller than your control group. So difference in population between treatment and control group are quite normal. Then I varied the baseline rate in the control group to be either 2.5, 25, or 250 per 100,000, so low, moderate, or high mortality rates. Now recall we got a null effect, so the treatment group will have approximately the same rate as the control group. So for each of these scenarios, I then replicated the population 1,000 times. I simulated the data 1,000 times, and I applied all of the regression models that I have found from the review to that simulated data. I compared them with 2 comparison models, the formally correct Poisson regression with population offset, and then also an ordinary least squares regression in which the logged rate is the outcome and there's no population covariate. This OLS regression of logged rates behaves approximately similarly to a Poisson regression in certain situations, and is probably the recommended approach if you don't have raw data on deaths and counts. So I compared it with these 2. Once I'd done my simulation study, I then moved on to a real-world example, which is Japanese prefectural all-cause mortality data from the year 2015 for women aged 0 to 34. So this is basically a data set which contains 1 observation for each age group in each prefecture in Japan. The ages I categorized into 5-year categories, so 0 to 4, 5 to 9, and so on, up to 30 to 34. So if you have those categories, those 6 age categories in 47 prefectures, then you have a total of 282 observations. Now, the age profile of mortality in Japan is very clear, and so I ran a regression model with these age groups as categorical variables, that is, dummy variables for each age group, with 20 to 24 as the reference population. 2015 is a census year in Japan with no disasters, so we should expect that Poisson regression will give precise estimates of the relative risk for each age group relative to 20 to 24-year-olds with very low error. So let's look at this code for these simulations before we go on to the results. So here's my R code, and it's a little bit messy, so please forgive me. I'm not the best R coder in the world. So what I've done here is I've set a base population of 1 million, and I've made a little vector that contains the populations of the control group, 10, 100, 1,000, or 10,000. Then here I've made a vector which contains the population multiplier, which goes from 1 to 2 in steps of 0.1. I've set the simulation number to be 1,000, and then I control the rate to be either 2.5, 25, or 250 per 100,000. I make an output model which contains the primary results of different models. This is an outcome matrix. And then I start my loop. So my loop starts by going through the base rates and setting a base rate. Then it sets, here it sets the number of observations in the control group from that vector of control populations. Then we loop through the length of the population multiplier. So we go in steps from 1 to 2, in steps of 0.1. And then we begin replicating the actual data set. So we do 1,000 simulations of each of these conditions. So basically we are going to set one base rate, we're going to set one population of the control group, we're going to set one multiplier for the population of the treatment group, and then we're going to run 1,000 simulations of that set of numbers. So here we put that control information in the summary output matrix. Then we generate the number of the population, the number of control group population, and the multiplier, and so on. Then we generate the data. So this is the this is not actually pre-data. This is the control group data. It's generated with a Poisson distribution applied to the population size, and the deaths are a Poisson distribution applied to the population size with a rate, right? And the same in the treatment group. Then we do some summaries of the data to put into our output matrix, and then we start running all of the models that we obtain from our review. So starting with Poisson, and then going on to an ordinary least squares with log rates, and then the models that I found, right? These are all done here. In each case, the coefficient, whether it's significant, and the sign of the coefficient are put into the output. This is very sloppy code, I know, please forgive me. And then there's a little bit of explanation here, and then finally we output the results to a CSV file because I prefer to do my plotting in Stata rather than R. So that's the basic simulation. So if we just set our simulation, let's set our simulation number to 2, so that this runs quickly. I think it'll work. Let's not wait for the results. So run it and wait for a few seconds. While we're waiting for this to run, let's go and look at the Stata code. So I've opened the Stata data here. So let's go to the Stata data and look at it. Okay, so this is not in any particular order of prefecture, but it's by age. So for example, here we have people aged 0 to 4 in prefecture 22. We have the number of deaths in that age group in that prefecture, the population in that age group in that prefecture, and the crude rate. We also here have the national population, which if you want to standardize, you can do, but I don't recommend it. And then we have the next prefecture 28 with the age group 0 to 4, the number of deaths, and the population. Right now, if we go down, here's the 5 to 9-year age groups for each prefecture, and here's the 10 to 14, and so on. And these are the rates here these are the crude rates. They're not multiplied by 100,000. Prefectures in Japan are numbered from 1 to 47. 1 is Hokkaido, and 47 is Okinawa. And they go from north to south. So 2 is, I think, Aomori and so on. If you look at the larger prefectures like 14, that has a larger population numbers, right? I think Tokyo is 13 from memory. There you go, there's a much larger population of 0 to 4-year-olds in Tokyo. And with a larger population comes a larger death rate, right? So that's the data that I'm using. And then the code is very simple. So we generate the log of the population, and then we run a Poisson regression model with the log population as an offset, and categorical variables for by the age groups with 20 to 24 as our reference. Then this is the equivalent for the OLS with logged rates. We get the log of the crude rate and we put it into our model, a regression model of the logged rate against the categorical age group. And then here we put in all the different other models. So model 3 has got prefecture population as a weight. Model 4 puts the logged population as a covariate, and so on. And then for a little bit of extra fun, with this model 4, I examined the predicted mortality rates for Tottery, which is prefecture 31, just so we can see that there's lots of predicted negative deaths, right? And then we go through the other models. Okay, so that's the stated code. Now let's go back and look at our R. Oh, look, it's run. So our simulations are complete. So if we go and look at the test data, this is what the test data looks like. This is from the final run, so it'll have a population of 20,000. So this is observation number 1 here. There is a population of 999,620, and there are 2,544 deaths in that population. This is the log of the population here. It's in the control group. That's the rate, and then there's some other variables that we use for generating the models, right? So there'll be 10,000 control groups going down, 10,000 control observations, and then once we get down to past 10,000, going past, it's not. Now we've got the treatment population, and the treatment population is larger, right? It's double. It's about 2 million because this is the final data set from the simulation, and it has more deaths as a result, right? But the rate should be the same because there's an assumption of a null effect in this model. Okay, so that's the data that we're going to be using. And then I think you can run some models if you want with this, and you can see what happens. All right, and this is a plot of a very rough plot that I ran. The final plot here, which just shows some mortality numbers. So that's it. That's the simulation code. All of this is on my GitHub. There's a link at the end. So let's go back now and look at our results. Right, so let's look at the results. So this is the result, first of all, of the review of the MBER papers. The gray models, the gray parts here are the models that I'm using for comparison. So the Poisson regression model has deaths as the response. It's got a Poisson distribution with a log link. Population is put into the model as an offset, and there are no weights. And these are the models I found from my review of the MBER with some example papers. These are the numbers of the working papers, right? So for example, model 3 models deaths directly as a Gaussian distribution with population as a weight. Model 4 models deaths directly with log population as a covariate and no weight. Model 5 has an inverse hyperbolic sine of deaths, which is surprisingly common, which is modeled as a Gaussian distribution with log population as a covariate. Note that these come from the same paper. I actually found this in the footnotes of the table. So in the text, they say they modeled deaths directly, but then in the footnotes of the tables, you discover that they didn't. They used an inverse hyperbolic sine transform. I'm not sure why. Then here, model 6, we have the log of deaths plus 1 with population as a covariate. Now, the reason for putting death plus 1 here is that if your deaths are 0, then the log doesn't exist, right? So you just add 1 to the deaths, and then the log is 0, right? But what this is basically doing is it's transforming your data so that observations where there were no deaths become observations where there was a death. And I don't think that's a good approach. Then here, this model, we have the rate modeled directly with population weight. And here we have the log rate modeled directly with square root of population as the weight. So a lot of different model approaches, right? So I applied all of these to my simulated data. And this is the result from one such simulation. So from the code, you see there are a lot of different simulations that I used. I'm not going to present all 20 of them here. You can run them yourself and play around with them. This is just one example. So this is when the control group has a sample size of 10. There's an equal population in the treatment of the control group. There's a low mortality rate of 2.5 per 100,000. And the population in each unit is approximately 1 million in both control and treatment. So here I've got the average treatment effect from my 1,000 simulations. Here I've got the range of possible treatment coefficients that could have come out of the model. Here I've got the percentage of models where the treatment effect is given its correct sign, and here the percent that are significant. Now recall that there is no treatment effect. The treatment and the control group have the same rates, so you should expect that the estimated treatment effect will be approximately 0 in the Poisson model, which it is. The range is not large, and remember this is a null model, so there should be no significant results, but because we're using p of 0.05 for significance, we expect 5% of our results to be spuriously significant. The Poisson regression model gets the correct sign 100% of the time. Now, if we go down and look at some of the econometric models, we can see a wide range of different average effects. They're all negative in sign, but they're much larger for these two models. In fact, they're larger for all of these three models, and much smaller for this model. Right? We can also see some wider ranges here. So this goes from -8 to 7, around a value of -0.15. That's maybe not too surprising. If you look at the ratios here, the average treatment effect is -0.006 in the Poisson model, and the range starts at -0.3. So about 2 orders of magnitude larger, right? This range starts 2 orders of magnitude larger than its treatment effect. So it's kind of to be expected, right? And actually 1 order of magnitude larger. And the same here. Here as well, the range is kind of similar, but then here we can see also 1 order of magnitude larger for the range. So they're all behaving in approximately the same way. They're just completely randomly different values. Also note that these models are much less likely to get the sign correct than the Poisson regression model. And they have a similar level of spurious significance. Now let's go and look at a different scenario where the populations are not equal. So here, for example, we have a sample size of 1,000 in the control group, and the treatment population is 1.5 times the control population, still with a low rate, and the control units having approximately 1 million people. As you would expect, the sample size is larger, so the Poisson estimate is even smaller in magnitude, the average. 99.9% of the time the sign is correct. Spurious significance remains at 5%. The ordinary least squares model of the logged rate is not behaving so well. The average treatment effect is much larger, even though it should have the same interpretation. And it gets the sign wrong about 70% of the time, and it's spuriously significant 12% of the time. But if we look through some of the other models, we start to see some very strange behavior. So these econometric models that we see here, for example, model 3 has an average treatment effect of 12.5. So in this simulation, it was -0.15. Now it's 12.5. And it's very precise. It's between 11.76 and 13.21. It's very precise. You can see that the range is in the same order of magnitude as the effect. But it's only correct in sign 50% of the time, because 50% of the time, the effect is negative. But it's only correct 50% of the time. And it's spuriously significant 100% of the time. These other models as well, you can see weird behavior. So now this model 4, the average treatment effect is close to 1, and the ranges from 3 orders of magnitude negative, larger and negative, to 3 orders of magnitude larger and positive, and it only gets the sign correct 50% of the time. In fact, these 4 models all get the sign correct 50% of the time. So basically what's happening here is that when an econometric model that uses one of these approaches, when an econometric paper that uses one of these models presents the coefficient and says there was an increase in blah, there's actually a 50% chance that they're wrong, and there was a decrease in blah. That's not cool, I think. So you can see these models just behave completely differently depending on the population size, right? In the treatment group compared to the control group. Now here the treatment is 1.5 times the control population. Recall I gave examples before of models where the treatment population might be 5 or 10 times larger or smaller than the control population. So we should expect that these are minimal estimates of how badly these models behave. I was interested in how these models behave, particularly models 4 and 6, which seem to give very strange results for the sign and which have ranges of values which scale with the population size, right? So I thought I'd check what they do. So I plotted the coefficient estimates for model 4 and model 6 for a moderate rate. I plotted them against the true relative risk. So the true relative risk is the average mortality rate in the treatment group divided by the average mortality rate in the control group. I plotted them here against the true relative risk. The colors here correspond with the ratio of population in treatment and control group. So blue is when the treatment group is 1.7 times the population of the control group. 1 is when they're the same size. And you can see that the magnitude of these coefficients increases with the ratio of the populations. When the ratio of populations is 1 in both these models, the coefficient is approximately 0. But when the ratio of the populations goes up to 1.7, in model 4, the coefficients range from minus 2,000 to 2,000. And in model 6, the coefficients range from minus 7 to 7. They scale up with the ratio of the populations. So what these models are actually estimating with the coefficient for the treatment group, for the treatment effect, is they are measuring the difference in population between the two groups. They're not actually measuring the effect of the treatment. That's a huge problem, right? That is a huge problem in these models. I also checked model 7 to see how its coefficients behave. There is a relationship between the coefficient and the true relative risk, as you can see here. So again, I've plotted the coefficients against the true relative risk, but you can see that the slope of that relationship depends on the base rate. So these models do not properly estimate the coefficient. They depend on the base rate. So to some extent, the coefficient of the treatment effect is actually incorporating information about the basic rate of the control group. It's not purely measuring the treatment effect. Remember, these are null models, so there should be no treatment effect. So I think that's a dismal failure. Finally, I applied these models to the Japanese mortality data. So the first row here is the Poisson regression model. The way that we can interpret this, the coefficient here is the logged rate in the 20 to 24-year-old age group. If we exponentiate this, we'll get the mortality rate in the 20 to 24-year-old age group. And then these other coefficients here are the logged relative risk of mortality in this age group relative to the 20 to 24-year-olds. So for example, 0 to 4-year-olds have about 2.5 times the risk of death as 20 to 24-year-olds. It's a classic J curve, right? Now, these are very precise and very good estimates of the true mortality profile in Japanese women. Now let's look at some of the other econometric models and how they handle this extremely well-structured, well-behaved Japanese mortality data. Model 4 has a constant of minus 165, and this arbitrary kind of numbers here for the age groups. Model 3 has a positive coefficient, a positive constant, and then these quite large and arbitrary values here for the coefficients. I don't know how to interpret these. I don't think you can interpret them easily. And you can see, in contrast here, these numbers are orders of magnitude smaller, right? So there's no real agreement between the estimates of the age profile from these econometric models and the formally correct one, right? That's also a problem. I applied model 4 to Totteri's data, and I'll show you the results of that in it's in the appendix of these slides. Okay, so let's briefly talk about what all of this means. So in my review, I found a wide range of models with no coherent justification for any of the decisions made in those models. There are wild differences in the values of the coefficients, how we interpret the coefficients, and the precision of those values when I applied these models to simulated data. I also found a high risk of false findings with the sign wrong in up to 50% of results from some of these models, and a high likelihood of significant findings where there shouldn't be any in some of these models. Basically, these models can't even handle a null situation where you're comparing populations which have equal rates and no difference in mortality between the populations. So they're very poorly behaved. When I applied them to Japanese mortality data, they were uninterpretable in many cases. There was no agreement on values between the models, and they could not describe a basic age profile of mortality in Japan. Only the sign was reliably correct. So basically, these models are physically meaningless. They're not describing mortality. They're not describing any relationships that we can understand. They're just arbitrarily spitting out numbers, which sometimes look right. And the implications of this are quite bad, because these models of death in econometrics are very bad. They're inconsistent between researchers. They're not statistically justifiable, and they're generally not interpretable. I could not find a paper in the NBER which used the correct method for analyzing mortality data. So what you should be assuming if you're reading econometric models is that most of the findings on mortality-related studies in those models are wrong. And I think most of these papers should be retracted. And before I give a final slide, I just want to show you the effect in Tottery. So I applied Model 4 to estimate predicted mortality rates in Tottery. And this is the result here. So basically, the mean predicted deaths in the prefecture of Tottery from Model 4 are negative. So in 20 to 24-year-olds, we predict minus 9.5 deaths, with a confidence interval ranging from minus 13 to minus 5.7. Now, I don't know if you've been to Tottery. It's a small and very nice prefecture. I lived there for 6 months. I studied Japanese there. It's a very nice place. It doesn't have many people. And when I was there, I certainly did not notice the dead rising from their graves. I'd never heard any news reports about reincarnation or resurrection. This model is nonsense. You cannot describe a prefecture of Japan with a stupid little model like this that predicts negative deaths. It's not a physically meaningful model. Now, this is Model 4, and Model 4 was about can economic policies reduce deaths of despair? Right? So I don't know, would you be despairing if you're coming back from the dead? Depends if you're a zombie or a vampire, I guess. These are the other models I found, and you can see they cover some quite interesting and important topics, but they're not doing it in a way that's meaningful. So thanks for watching this video. This QR code here is a link to the GitHub, which contains the code I used and the data, if you want to reproduce this yourself. And also this research, when I presented at EcoSta, not when I put it on YouTube, but when I presented it at EcoSta, was supported by the JSPS, a research grant that I've got to study this kind of information. So thanks very much for your time today, and I hope you learned something about how much you can trust these models. Thank you very much.